Buffers and pH is the name of the topic for today. Here's a picture of Bufferin, which you can buy at any CVS or Walmart. And it's called buffered aspirin. And it is less harsh on your stomach because aspirin itself is an acid, and you'd be adding an acid to your stomach acid when you take an aspirin. So if you take Bufferin, you're taking aspirin, and yet it is much gentler on the stomach. The common ion effect is the shift in equilibrium caused by the addition of a compound having an ion in common with the dissolved substance. The presence of a common ion suppresses the ionization of a weak acid or a weak base. Consider a mixture of sodium acetate, which is a strong electrolyte, and acetic acid, which is a weak acid. Now, I notice for the sodium acetate, it dissociates very well into sodium and acetate ions, whereas acetic acid does not ionize very well in water. It just produces a few hydrogen ions and acetate ions. But the common ion is the acetate ion. And what happens if I add sodium acetate to acetic acid? It causes a shift to the left because I'd be increasing the acetate, which would cause it to go in that direction. Now here's that equation again that I had in the last slide. I have my acetic acid in equilibrium with the acetate and the hydrogen ions. If I add acid to this system, it's going to cause a shift to the left. Now we see that here. Go back a bit. It'll cause a shift to the left because you're increasing the hydrogen ions. It'll have to go in that direction. Now notice when it goes in that direction, this concentration goes down while the acid concentration goes up. What happens if I add a base to this system? Well, the hydroxide ions will combine with the hydrogen ions to form water, and thus this will cause a shift to the right. And as it shifts to the right, this concentration, the acetate, will go up, and the acetic acid concentration will go down. So what we see is that one of these is going up while the other is going down. And many times you have to figure out which one is changing in which direction. A buffer solution is composed of a weak acid or a weak base and the salt of the weak acid or the weak base. So it's the weak acid and its salt or the weak base and its salt. Both have to be present. And this was actually a buffered solution that you would get maybe in a hospital. So which of the following solutions can be classified as buffer systems? So we have two systems here. This is potassium dihydrogen phosphate, and this is phosphoric acid. This is sodium perchlorate, and this is perchloric acid. So we'd have to look up both of these acids to see, for instance, if one was strong or one was weak, because we need to have a weak acid. And then we'll look over here to see, do I have its conjugate needed? So if this is a weak acid, is this going to be a conjugate base that we could use? So I'm going to take a couple of minutes and figure that out. Now when you're ready, just go to the next slide. So, what constitutes a buffer system? Which of the preceding solutions contains a weak acid and its salt, containing the weak conjugate base? Which of the preceding solutions contains a weak base and its salt? Why is the conjugate base of a strong acid not able to neutralize an added acid? All good questions. Let's check out the solution. The criteria for a buffer system is that we must have a weak acid and its salt, or a weak base and its salt. The H3PO4 phosphoric acid is a weak acid, and its conjugate base, dihydrogen phosphate, is a weak base. Therefore, this would be a good buffer system. But for B, because HCl4 is a strong acid, and its conjugate base is an extremely weak base, this means that the perchlorate ion will not be able to combine with a hydrogen ion in solution to form perchloric acid. So this system cannot act as a buffer system. The minute you saw that you had this strong acid in there, you would just say, no, it can't be a buffer system. So this is just, again, a little definition for buffers. Over here, we have some Alka-Seltzer tablet dissolving in water that also contains a buffer. So let me go through finding the pH of a buffer system, and then we'll add something to that system to see how it'll affect the pH. So in this case, I'm going to be using HAC to represent acetic acid, just because it's shorter. This is constant. So this is my little equation for it. So here's acetate, acetic acid, hydrogen ions. This tells me it doesn't dissociate very well to the right. So if I start off with equal molarities, in this case to both 0.1 molar, what would the pH of the buffer system be? Here's my equilibrium expression. I have my products over my reactant. I would just make a substitution now. Notice I don't know what the hydrogen ions are. So this will have to be X, 0.1 here and 0.1 there. And notice then I could cancel out the 0.1s. So 1.8 times 10 to the negative fifth is my hydrogen ion concentration. And then taking the negative log of that, I could get the pH. So the pH is 4.74. So 4.74 is the pH of a buffer system for this acetic acid and its salt. Notice that I had equal concentrations of these guys. That's important. You have to have enough so that they can react in either direction depending on what's being added to it. For instance, here. So let's say now, here's my same buffer system, and this time I add 0.02 moles of hydrogen ions. Which direction would be shifted when I do? Well, remember, here's the hydrogen ions. If I increase this concentration, I would shift away from it. So this guy would go down and this one would go up. So the shift would be to the left. Now, how much will they go up and down by? By what I added. So one of them will be, I'll be adding 0.02 moles to it, the other one subtracting it. So as I mentioned, a shift to the left causes the acetate concentration to go down by what I added, and causes the acid concentration to go up by what I added. Those are my new concentrations, and now I will find the hydrogen ion concentration like I did previously, and then the pH. So now when I set it up, I got to make sure, and I'm just kind of using the same expression here, just to cut down on space. And before I follow through with the math, let's go back and just see what makes sense. If I have a buffer system and I added acid to it, the pH must fall a bit. The buffer, though, will stop it from falling very far. What does that mean? Well, if I started with a pH of 4.74, the pH of my system now has to be a little bit less than that. So if I got a number bigger than 4.74, I go back and check my math. I probably have these numbers in the wrong place. So this is my hydrogen ion concentration, which I would get by multiplying 1.8 times 10 to the negative fifth by 0.12 and dividing the answer by 0.08. And now when I find the pH, you notice it did become less, as I would expect, but not a great deal less. Can you do this one on your own? Calculate the pH of a buffer system containing 1.0 molar acetic acid and 0.85 molar sodium acetate. Here's the equation that we had before. I just had used HAC instead of using the acetic acid formula. You can go from here. And then the second question, what is the pH of the buffer system after the addition of 0.10 moles of sodium hydroxide to the solution? So in this case, pause the PowerPoint video, try these two problems, and come back and check out the solution. Okay, here we go now. So here's my equation, my constant. Initially, 1.0 moles of my acid, 0.85 moles per liter of my base. Find out what X is. Notice that I wind up taking my constant, they are here, dividing by 0.85, and I get that for my hydrogen ions, and I find the pH is 4.67. All right, just like I had done before. Now, what about when I add my 0.1 moles of hydroxide? So when you add the 0.1 moles of hydroxide, it's going to react with the hydrogen ions, causing a shift to the right to replace them. I don't know what this will become. That's what I have to find out. Now this one will go down, this one will go up. That I do know. So, and they'll go up and down by the amount that I added. So what is it at equilibrium? 0.9 and 0.95. Solve it the same way I did before. My expression, I replace my acetate with this concentration and my acid with this new concentration. Solve it for X, and I get 1.7 times 10 to the negative fifth for my molarity for the hydrogen ions. Now remember, I do expect the pH to go up a bit because I added the base. The pH is 4.77, and prior to this, it was 4.74, I believe. Okay. Now let's consider a mixture of a salt, sodium. This could be sodium acetate, but it's sodium with an anion anyway, and a weak acid. So here's the equation for my salt, my sodium, and whatever it is here. Let's call it acetate, and dissociating in water. And this is my weak acid. And we saw this before with sodium acetate and acetic acid, but this would represent now any weak acid in salt. So that goes 100%, and this doesn't. So my constant would be equal to that H positive times A negative over HA. If I solve it for the hydrogen ion concentration, I would get this. Then taking the negative log of both sides, I'd have the negative log of the hydrogen ion concentration would equal the negative log of Ka minus the log of the acid over its base. And if I want to have plus the log instead of minus the log, I just have to switch these. So that's the conjugate base over the acid. And then I can replace both of these with what they're equal to. So you can find the pH of the P of anything, I should say, which just means taking that number and making it into a power of 10. So the negative log of Ka equals what we call the pKa. And the negative log of the hydrogen ions is called the pH. Now I have some things I've seen before. This equation is called the Henderson-Hasselbalch equation. And it's used a lot of times to find the ratio between your conjugate base and acid that you need to make up a pH of a particular number. We're going to be using it coming up. So if you want to replace, I would say this value with these two kind of spells it out better. So this is your Henderson-Hasselbalch equation. We're going to be using that now. These are three of the things that you can use the equation for: to find the pH of a buffer system, to decide on an appropriate buffer to be used for a system, and then find the ratio of base to acid that you have to use to make up your buffer. So here's a question. What is the pH of the buffer system where HAC equals 0.12 molar and the acetate is 0.08 molar? Using the Henderson-Hasselbalch equation, and we have our constant. So we want the pH of the buffer system. So here's my equation. Initially, that's what I have. So this is the molarity of the HAC, and that's the acetate. Here's my equation. So my equation here, and I have my Ka, so I can plug in my Ka in here, in here actually, and then I can find the negative log of that. So what do I have then? The negative log of the Ka is going to be this, and then I have plus the log 0.08, and that's my acid, my conjugate base, over 0.12, that's my acid. So I would solve this, and then find the log of that, and then add it to the log here. So the negative log of this value is 4.74. And then once I divide and then take the log of this, I get negative 0.18. When I add them together, I get 4.56. So make sure this makes sense. So if you go up here, you see, okay, the acid concentration was a little bit higher than the base. So I'd expect my system to be a little bit more acidic than basic. And that seems to fit pretty well. Describe how you would prepare a phosphate buffer with a pH of about 7.40. For a buffer to function effectively, the concentrations of the acid component must be roughly equal to the conjugate base component. According to the Henderson-Hasselbalch equation, when the desired pH is close to the pKa of the acid, that is, when the pH almost equals the pKa, or when this is true, the log of 1, when the log is equal to 0, that means this concentration is equal to 1. So what they're really saying is, if we want this to be true, then this really has to be true, that these concentrations have to be about 1. Now I mentioned this in the beginning of this video, that the usual ratio between the base and the acid that you want to have for the buffer is going to be about 1. And this way you have enough of both components so that they can react with acids or bases that are entering the system. So I just left up, this is a question, but I left out up here for a reason, which you're going to see. So in our solution, because phosphoric acid is the triprotic acid, we're going to write the 3 stages of ionization as follows, and the pKa values found by applying this. So I get this all done out, and I'll show you how we decide how to come up with the acid and the base. So here's the first ionization reaction. Phosphoric acid ionizes 1 hydrogen at a time. That is a constant for it. The second one, so when this is an acid, it ionizes similarly. You notice that the constant is a lot smaller. And then for the last one, you get a very small constant. What about the pKa's of all these 3 values? Remember, we want the pKa to be pretty much that, or close to it. So what do we see here? Look at the middle one. Pretty close. So the most suitable of the 3 buffer systems is the middle one, as I just pointed out, because the pKa of the acid, H2PO4-, is closest to the desired pH. So we know that. So now we can plug in our pH and our pKa and work to come up with the ratio between these two. So if I take 7.41 and divide it by 7.21, I get 0.19. Taking the anti-log of 0.19, I get 1.5. So what does 1.5 mean? It means that one way to prepare a phosphate buffer with a pH of 7.40 is to dissolve disodium hydrogen phosphate, because we need the HPO4 minus ion, minus 2 ion. We need that, this guy. And so we would dissolve enough of this and sodium dihydrogen phosphate, which will give us the acid, in a mole ratio of 1.5 to 1. That's why we got this. For example, we could dissolve 1.5 moles of sodium hydrogen phosphate, disodium, I should say, hydrogen phosphate, and 1 mole of sodium dihydrogen phosphate in enough water to make up a liter of solution. And then the molarities would be 1.5 to 1, just that ratio. So this is how it's done many times. People know the pH they want to have, and they look for an appropriate buffer to give them that.